Write each of the following in the form of a root b, where b is prime. Root 32, root 45, and root 75. So root 32 can be broken down as root 16 times 2, because 16 times 2 is 32, which can be factorized as root 16 multiplied by root 2, and the square root of 16 is 4, so we've got 4 root 2. And that works because 2 is indeed a prime number. So the square root of 32 is the same thing as 4 root 2. Root 45 can be broken down as root 9 times 5, because 9 times 5 is 45, which factorizes as root 9 multiplied by root 5. The square root of 9 is 3, so we get 3 root 5, which works because 5 is a prime number. So root 45 is equal to 3 root 5. And then the square root of 75 can be rewritten as the square root of 25 times 3, because 25 times 3 is 75, which gives us root 25 times root 3. The square root of 25 is 5, so we have 5 root 3, which works because, again, root 3 is a prime. Express the following in the form of a over b, where a and b are elements of the natural number set. So root 9 over 4, root 2 and 7/9. And express 10 over root 2 in the form of k root 2. So root 9 over 4 is the same thing as root 9 divided by root 4. Square root of 9 is 3, square root of 4 is 2, so we get 3 over 2. Which works because 3 and 2 are natural numbers. Next we have the square root of 2 and 7/9. Well, 2 and 7/9 can be rewritten as 25 over 9, so we get the square root of 25 over 9, which is root 25 over root 9, which is 5 over 3, and 5 and 3 are both natural numbers, so that works perfect. Then 10 over root 2, well, we don't want a fraction, and really what we're trying to do is rationalize the denominator, because we want to end up with something times root 2, so we don't want a fraction, so we don't want a surd in our denominator. So we're going to rationalize the denominator by multiplying above and below by root 2. So multiplying the top and the bottom by root 2, you're really multiplying by 1, because anything divided by itself is 1. So 10 times root 2 is just 10 root 2, and root 2 times root 2 is 2, and 10 divided by 2 is 5, so you get 5 root 2. Express root 18 plus root 50 minus root 8 in the form of a root b, where b is prime. So root 18 can be rewritten as root 9 root 2. Root 50 can be rewritten as root 25 root 2. And minus root 8 can be rewritten as minus root 4 root 2. The square root of 9 is 3, so you get 3 root 2. The square root of 25 is 5, so you get 5 root 2. And the square root of 4 is 2, so you get minus 2 root 2. Then 3 plus 5 minus 2 gives us 8 minus 2. So 3 plus 5 gives us 8. So we have 8 root 2 minus 2 root 2. And 8 minus 2 is 6 root 2. Then root 20 minus root 5 plus root 45 can be rewritten as root 4 root 5 minus root 5 minus root 9 root 5. Because 4 times 5 is 20, and 9 times 5 is 45. Now 5 is a prime number, so it doesn't have any other factors. So the square root of 4 is 2, so we get 2 root 5, minus root 5 just stays the same, and the square root of 9 is 3, so we get 3 root 5. Now 2 root 5 plus 3 root 5 is 5 root 5. And we're going to minus this root 5, which is really minus 1 root 5. And 5 minus 1 is 4, so we get 4 root 5. So if we let 4 root 5 equal to k root 5, we can cancel out the root 5's, and k is equal to 4. So part 1, we had to express this in the form of a root b, where b is prime. We got 6 root 2. And part 2, we were told that this is equal to k root 5. We're told to find the value of k. The value of k is 4. Conjugate surds. A plus root b is a compound surd. It just means it's got two parts in it. Its conjugate is a minus root b or minus a plus root b. Root a minus root b is a compound surd. Its conjugate is root a plus root b or minus root a minus root b. They have the same components with one of the signs changed. The product of a surd and its conjugate is always a rational number. So product means multiply. So if we multiply a surd and its conjugate, we always end up with a rational number. So think of the difference of two squares. So for example, a minus b multiplied by a plus b ends up giving us a squared minus b squared, which is rational. Okay, so in our example, show that minus 1 plus root 3 over 1 plus root 3 is equal to 2 minus root 3. So we have a fraction and there are surds involved. So we're going to multiply above and below by the conjugate of the denominator. So this is the denominator, 1 plus root 3. So its conjugate is 1 minus root 3. So we multiply the top and the bottom by 1 minus root 3. Then multiplying fractions, we do top by top, bottom by bottom. So minus 1 times 1 is minus 1. Minus 1 times minus root 3 is positive root 3. Root 3 times 1 is root 3. And root 3 times minus root 3 is minus 3. So just to show the rough work for that, where the minus 3 comes from. So root 3 multiplied by minus root 3 is minus root 3 root 3. And root 3 times root 3 is 3. And then you've got the minus stuck on in front. So then the bottom, 1 times 1 is 1. 1 times minus root 3 is minus root 3. Root 3 times 1 is root 3. And root 3 times minus root 3 is minus 3. Worked out in the same way as that other's minus 3. Then we simplify. Minus 1 minus root 3 is minus 4. And root 3 plus root 3, well that's really 1 root 3 plus 1 root 3. And 1 plus 1 is 2 root 3. Then on the bottom, 1 minus 3 is minus 2. And then minus root 3 and positive root 3, they will just cancel out. So we have minus 4 plus 2 root 3 over minus 2. Minus 4 divided by minus 2 is 2. 2 divided by minus 2 is minus 1. So you can say you've got 2 minus 1 root 3, or just 2 minus root 3. Note, we could have also multiplied the top and the bottom by minus 1 plus root 3, which is also the conjugate surd of 1 plus root 3. So instead of multiplying by 1 minus root 3 on top and bottom, we could have multiplied by minus 1 plus root 3. So what did we do? Well, we multiplied the top and the bottom by 1 minus root 3, which is the conjugate of the surd 1 plus root 3. That was our first step. So we multiply the top by the top and the bottom by the bottom, because we're multiplying fractions. Top by top, bottom by bottom. Next we simplified the top and the bottom, and then we divided each part by minus 2. In the diagram, the rectangle Q or ST has sides TQ equals 3 plus root 2 centimeters and TS equals 3 minus root 2 centimeters. So here is the rectangle Q or ST. TQ is 3 plus root 2 centimeters, so SR must be the same. And TS is 3 minus root 2 centimeters. So QR must be the same as well. Part 1. Find the length of the perimeter P of the rectangle where P is an element of n, the natural number set. So P is a positive whole number. So I've drawn out the rectangle again. and labelled 3 plus root 2 and 3 plus root 2 for the widths, and then 3 minus root 2 and 3 minus root 2 for the lengths. So we have 3 plus root 2 plus 3 plus root 2 plus 3 minus root 2 plus 3 minus root 2. So then you can just basically forget about all the brackets because you're not multiplying anything into the brackets, so you just bring everything down, 3. So then positive root 2 and minus root 2 will cancel, and positive root 2 and minus root 2 will cancel as well. So we end up with 3 plus 3 plus 3 plus 3, which is 12 centimetres. So the perimeter is 12 centimetres. Part 2, find the area of the rectangle A, where A is an element of the natural number set. So we know that area is length multiplied by width. So we're going to do 3 plus root 2 multiplied by 3 minus root 2. So 3 plus root 2 multiplied by 3 minus root 2. So we're going to crack open our egg. We're going to bring down the 3, stick on this second egg, stick on the 3 minus root 2, bring down the root 2, stick on the egg. 3 times 3 is 9. 3 times minus root 2 is minus 3 root 2. Root 2 times 3 is 3 root 2. Root 2 times minus root 2 is minus 2. Because root 2 times minus root 2 is minus root 2 root 2, which is just minus 2. Now the minus 3 root 2 and the positive 3 root 2 will cancel, and 9 minus 2 is 7 centimetres, and make sure it's squared. Part 3. Find the length of the diagonal SQ equal to root k, where k is an element of the natural number set. So you need to find the length of this diagonal. So hopefully you notice that this forms a right-angled triangle, and the formula for that is Pythagoras' theorem. So Pythagoras' theorem is c squared equals a squared plus b squared, where the c is the longest side. So the c is going to be SQ. So we're going to swap c squared for SQ squared. And then the a and the b, it doesn't matter which way you label them. So SR I'm going to label as A, and QR I'm going to label as B, but it doesn't matter. So A squared becomes SR squared, and B squared becomes RQ squared. Now SR is 3 plus root 2, and RQ is 3 minus root 2. So we're going to have 3 plus root 2 squared, which will become 3 plus root 2 times 3 plus root 2, plus 3 minus root 2 squared, which will be 3 minus root 2 times 3 minus root 2. So 3 times 3 is 9. 3 times root 2 is 3 root 2. Root 2 times 3 is 3 root 2. So we end up getting 6 root 2. And root 2 by root 2 is 2. Then 3 times 3 is 9. 3 times minus root 2 is minus 3 root 2. Minus root 2 times 3 is minus 3 root 2, giving us minus 6 root 2. And minus root 2 times minus root 2 is positive 2. So minus root 2 times minus root 2, well, a minus by minus is a plus, so it's plus root 2, which is going to be just plus 2. So then 6 root 2 and minus 6 root 2 will cancel, and 9 plus 2 plus 9 plus 2 is 22. So if SQ squared is equal to 22, then SQ will be equal to the square root of 22. So we just leave it as root 22 centimetres. Because we wanted our answer in surd form, where k is an element of the natural number set, and 22 is indeed a natural number. If x equals root a plus 1 over root a, and y equals root a minus 1 over root a, where a is greater than 0, find the value of the square root of x squared minus y squared. So x squared is going to be root a plus 1 over root a multiplied by itself. So root a plus 1 over root a multiplied by root a plus 1 over root a. So we're going to crack open the first egg. We bring down the root a. We stick on the root a plus 1 over root a. We bring down the 1 over root a, and again stick on the root a plus 1 over root a. Root a times root a is a. Root a times 1 over root a is 1. 1 over root a times root a is 1. And 1 over root a times 1 over root a is 1 over a. And then 1 plus 1 makes 2. So x squared is a plus 2 plus 1 over a. So just to show you where that 1 came from again, both of those ones, root a times 1 over root a is the same thing as root a over 1 times 1 over root a. Top by top, bottom by bottom. Root a times 1 is root a. 1 times root a is root a. And anything divided by itself is 1. So that's where both of those 1's come from. Okay, next is y squared. So if y is root a minus 1 over root a, then y squared is going to be root a minus 1 over root a multiplied by itself. So we have root a minus 1 over root a multiplied by root a minus 1 over root a. So we crack open the first egg. The root a comes down. It's stuck on to root a minus 1 over root a. Then the minus 1 over root a comes down. And again it's stuck on to root a minus 1 over root a. Root a times root a is a. Root a times minus 1 over root a is minus 1. Minus 1 over root a times root a is minus 1. And minus 1 over root a times minus 1 over root a is plus 1 over a. And then minus 1 is minus 2. So y squared is a minus 2 plus 1 over a. So we worked out x squared to be a plus 2 plus 1 over a, and y squared to be a minus 2 plus 1 over a. So we were asked to find the value of the square root of x squared minus y squared. So the square root of x squared minus y squared will be the square root of a plus 2 plus 1 over a, because that's what we got for x squared. Swapping that x squared for that. Then we have our minus, and then y squared is a minus 2 plus 1 over a. So we bring down the a, the 2, and the 1 over a. Minus times a is minus a. Minus times minus 2 is plus 2. Minus times plus 1 over a is minus 1 over a. We still have the square root. A and minus a will cancel. 1 over a and minus 1 over a will cancel. And 2 plus 2 is 4. And the square root of 4 is 2. So the value of the square root of x squared minus y squared is actually 2. So this is method 2 using the difference of two squares. Well, we know that x squared minus y squared can be factorized as x minus y times x plus y using the difference of two squares. So if we swap x for root a plus 1 over root a, then bring down the minus and swap y for root a minus 1 over root a, and multiply that by x, again, which is root a plus 1 over root a, plus, bring down the plus, y, which again is root a minus 1 over root a. So we came up with a little formula using the difference of two squares in terms of x and y, and we just subbed into it. So we bring down the root a, bring down the 1 over root a, minus times root a is minus root a, and minus times minus 1 over root a is plus 1 over root a. Then we bring down the root a, bring down the 1 over root a, plus times root a is plus root a, plus times minus 1 over root a is minus 1 over root a. Remember, there's brackets around this and brackets around this. So root a minus root a will cancel, and 1 over root a plus 1 over root a becomes 2 over root a. So this is just showing you where that came from. So 1 over root a plus 1 over root a is 2 of them. So 2, 1 over root a, which is 2 over root a. That's just showing you how this plus this gave us this. Then 1 over root a minus 1 over root a will cancel, and root a plus root a is 2 root a. And 2 over root a multiplied by 2 root a will give us 4, because 2 over root a stays as it is, but 2 root a is the same thing as 2 root a over 1. Top by top, bottom by bottom. 2 times 2 root a is 4 root a. Root a times 1 is root a. And the root a's will cancel, leaving us with 4. So if x squared minus y squared is 4, then the square root of x squared minus y squared is the square root of 4, which again is 2.